Alright, in this video we go over section 3.5, absolute extrema. So in this section we will find the absolute, we'll learn how to find the absolute maximum and the absolute minimum of a function. And well, the theorem here is that when we have a function that is continuous on the closed interval, then f will have an absolute max and an absolute min on this interval. Well, how is this different from what we did in the previous example, in the previous section, rather 3.4? Well, in section 3.4, we did this rel max and rel mins, but instead of having open or closed intervals, we did it over the open interval a to b. And well, graphically, this is essentially what we did. So we had a function like this polynomial function, this just to make things easier, for which the open interval was the entire domain of a function. And in this case, well, we'll look for this relative minimum, this relative maximum. But the reason why these are all relative is because technically, due to this arrow pointing up and this one pointing down, well, that leads to the fact that they go all the way up to positive infinity, which technically is the absolute maximum and their absolute minimum respectively. However, why would we care about those absolute max and mins that are, if we already know that they are infinity? Well, the problem here is that if for applications, those infinities, well, I mean, they are just by looking at the graph, it's easy to tell. However, we want to look for values for which there will be a relative max or a relative min. Now, that's what we did in the last section. In this section, the picture is that we have a function on a trimmed domain. So in this case, yes, we still have this relative max and this relative min. However, this minimum right here, there's also another minimum. There is this maximum and there is another maximum. This time we were looking for the absolute maximum, which is the highest of the maximum, and the absolute minimum, which is the smallest of the minimums. And well, the process to go about these examples will be a lot shorter than what we did in the previous example. So yes, we are still going to take a derivative, and we're going to find critical points. And in the end, instead of going over the entire table and testing the critical values, increasing, decreasing, no, we no longer care about those. The we're looking for the absolute max or the absolute min. You'll see how it works. So let's look at an example. We have the function f of x equals to x cubed minus 15x squared plus 24x plus 6 on the interval 0 to 5. Notice in this case we're looking for a function in a closed interval. Back in the previous section we were asked to find relative extrema, but without having a restricted domain. In this case, no, it's not restricted. In this case, we want to know between 0 and 5. So let's go ahead and do the calculus. So, by the way, the graph of the function is given right below, so you can see what the absolute max will be and what the absolute min will be. But of course, let's do the calculus to show how this works. So f prime of x, which is the derivative, that's going to be 6x squared minus 15x. Oh, actually not minus 15x, minus 30x plus 24. And well, we are supposed to set the derivative equals to 0, that is 6x squared minus 30x plus 24. And try to solve this equation, which is a polynomial equation, by factoring using any of the techniques that we have out there. And yes, the leading coefficient is different than 1, so you may be thinking of using either the diamond method or the guess and check, which may take a while. However, for polynomials that have the leading coefficient different than 1, usually it works to check if every single term in the polynomial is divisible by in this case 6, which is the leading coefficient. This way, so we can do a factoring in a way shorter and easier way. And in this case, the 6, the 30, and the 24, all of them are divisible by 6. And if we divide by 6, well, the right hand side, 0 over 6, that's going to give us a 0. And over here, x squared minus 15x, or actually minus 5x. Hold on. Something's not working here. Okay, minus 5x and plus 4. And this polynomial is naturally factorable, so that is we will look for factors of 4 that add up to -5, -1, and -4. And on the one hand, this will give us the critical value of x equals to 1, and this will give us the critical value of x equals to 4. Alright, what are we going to do this time? No, we're not going to do the first derivative test. We're not going to do a table like I mentioned before. So this time, our second step is to evaluate the original function at a and b, which are the endpoints of the closed interval, and c, which represents all critical values. So I'm going to do a table here for x, and I'm going to list number 1, the critical values. Well, actually, I'm going to do first the endpoints of the closed interval 0 and 5, and the critical numbers 1 and 2. I mean 4. And then we are going to evaluate this original function f of x, which is 2x cubed minus 15x squared plus 24x plus 6. And we are going to evaluate the original function at these 4 values. So on the one hand, let's see. So the lower limit, which will be f of, let's do f of 0. That's 2 times 0 cubed minus 15 times 0 squared plus 24 times 0 plus 6. Alright, this will be equal to, well, let me just highlight so you can see what am I highlighting and where. Okay, so the first 3 terms zero out, giving us at the end a 6. Okay, we will determine whether that will be one of the absolute max or the absolute min. Let's do the next one, the upper endpoint of the closed interval. So in this case, evaluate at 5, evaluate f of 5, 2 times 5 cubed minus 15 times 5 squared plus 24 times 5 plus 6, and that equals, well, using a graphing calculator, we can put this in, and that should give us a 1. All right, let's highlight whatever we are highlighting. I mean, we're evaluating rather. And the third evaluation will be with one of the critical values. Actually, all of them. Let's start with the first one. So f of 1 equals 2 times 1 cubed minus 15 times 1 squared plus 24 times 1 plus 6. And simplifying this should give us a 17. Actually, I don't like that 7. That looks like another one. 17. Okay, so let's do the last one. So we did it for one of the critical numbers. Let's do it again for the other critical number. So green, 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 and green, and that is f of 4 equals 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 plus 6 equals to negative 10 if we use a graphing calculator. So this is pretty much all we have to do for the calculations now. What the next is to look at the values that we obtain here. Notice in this case, we need to look at the smallest of the value and name that our absolute minimum. In this case, well, the smallest of the values that I highlighted in red is negative 10, which is going to be our relative, oh no, not the relative, actually. We're doing the absolute minimum. That's the absolute minimum. On the other hand, we need to look for the largest of the values, which in this case is the 17, and that's going to be our absolute maximum. And we're essentially done. That's all we have to do. Just be sure to express this as order pairs. In this case, well, it's the order pair 1, 17. And the other pair is for negative 10. And well, this is basically illustrated here in the graph. Here, notice, yes, this is a minimum point. This is also a minimum point. But one of these two minimums, it's an absolute minimum, you know, actually the one with the lowest value of y. So, what's going on here? Okay, let me do, yes. All right, so in this case, it's the one with the negative 10 for negative 10. And well, the graph also displays two maximums. This one maximum here, and then there's another maximum there. Well, out of those two maximums, there are two. There's two, you know, one of them is larger than the other one, and that's the one with the 17. So, and the other ones, these two, no need to do anything about them because ultimately we want only the absolute max and the absolute min. All right, so let's look at another example. For the next example, we will find the absolute extrema for the function f of x equals to x to the 2/3 plus 1 on the interval negative 8 to 8. All right, so let's see what we're going to get for this. Of course, take the first derivative of the function f prime of x equals 2/3 of x to the negative 1/3 using the general power rule, and then the derivative of 1 is simply 0. Well, we need to set the derivative equal to 0. That is, well, first of all, let's set this is 2 over 3x to the 1/3. Oh, actually, yeah, 2/3 minus 1. It's actually I did a mistake over here. 2/3 minus 1. That's oh yes, negative 1/3. That is correct. Okay, so that's fine. And in this case, well, 2 over 3x to the 1/3, set it equal to 0. And well, in this case, it's only the denominator that contains the x. So on the one hand, 2 equals to 0. That is the denominator, set it equal to 0, but this doesn't make sense. And the only one that we set is the denominator 3x to the 1/3. That equal to 0, and x equals to 1/3 when we divide both sides by 3, and essentially cubed both sides to get x equals to 0 still. All right, so that's the only critical value. So we're gonna make a table with listing the x values of number 1, the lower limit, the upper limit, and the critical values. So on the one hand, the lower limit, which is -8, and what else? The upper limit, which is 8, and the critical number, which is 0. Okay, so I'm gonna go with the function over here. However, I'm going to write this function in the following way. So one thing to recall, let me do something on the side. Well, let me do it above. So this x to the 2/3 is the same as the cube root of x squared, or even better, because it will be more convenient for our case, the cube root of x, the whole quantity squared. So I'm going to rewrite this function as f of x equals the cube root of x, quantity squared, plus 1. So f of x equals the cube root of x squared plus 1. Because in this case we have perfect cubes, so we do the perfect cubes inside of the parentheses first, and then we can square the number. That we don't get in trouble with when raising the powers. Now let's see. So we're gonna do f evaluated at the lower limit. That's the cube root of -8, quantity squared plus 1. Which is, well, the cube root of -8, be careful, that's a -2, and then that -2, square it, that's going to be a 4 plus 1, which will be equal to 5. And again, what are we doing? We are evaluating at -8, and let's do the next one, f of 8, that's the cube root of 8, rather, squared plus 1. And same quantity again, so that's the cube root of 8, which is 2, and then 2 squared equals to 4 plus 1, that equals to 5. And last but not least, f of, oh, by the way, let's highlight what are we substituting, and let's do the one for the critical value, the only one critical value, f of 0, that's the cube root of 0 squared plus 1. And well, the cube root of 0, which is 0, squared still is 0 plus 1, that's a 1. All right, now observe something very interesting here. Notice that in this case we got when we observe which one is the largest value and which one is the smallest value. Notice that the absolute value repeats. The absolute maximum repeats. That is correct. That is fine. Absolute maximum. If it repeats, it's fine. You can call it absolute maximum twice for it. And well, of course, the remaining possibility, which is a smaller number, that is 1, that's going to be indeed the absolute minimum. And of course, this is illustrated in the graph right here. Notice how the absolute maximum is, there's one over here, and there's another there, as opposed to the absolute minimum, which is right here, the lowest point on the graph. That is, well, in this case, notice we're not using the entire graph, because technically this graph goes on forever on one side, goes on forever on the other side, but it is not the case. We're not looking at the entire graph, only at the portion of graph that contains the interval from -8 to 8. And well, like I mentioned before, these kind of problems typically are a lot shorter than the ones that we did in the previous section. And well, so these were a couple of examples on how to find the absolute extrema for this function. All right, so I think this is a good place to quit, and I'll see you in the next video.